So while the empirical rule is good for getting an idea of how the areas are distributed under the curve, it really is just for estimates. So we're not getting exact values there, and that's where we're going to go to technology to help us out. So what we'll be able to do is if we have a bell-shaped curve or if we have normally distributed data and we know the mean and standard deviation, we can use Stapplet to find any area under the curve, which will answer questions involving probability or percent chance or things like that, since area under the curve is going to represent our probabilities. Okay, so let's go to stapplet.com. And then we're going to go to probability and open up normal distribution. So something here at the top is operation. There's going to be two choices here. And what we need to keep in mind is if we're looking for probability, we want to calculate an area under the normal curve. So any questions where we're looking for some percent chance, we want this option of calculate an area under the curve. And then from there, we're going to set our mean and standard deviation based on the information of our question, which we're going to go with that mean of 40, standard deviation of 8. And when we plot the distribution, it'll show us our bell-shaped curve. It's going to number the number line following our standard deviations and mean, which is really nice. So we get a nice visual. And then down here at the bottom, we can start calculating different areas. So we can go for an area between two values, to the left, to the right, and then outside of a region. And then all we need to set are these boundaries, which I also call cutoff values every now and then. It's what's going to cut off the area that we're finding. So on our worksheet here, I tried to outline when you'll choose different possible areas. So like calculating the area between two values, it's when we're looking to be restricted between two. To the left of a value is if we're doing like less than or equal to, or at most. And calculating the area to the right will be more than or equal to, or at least cases. And then calculating the area outside of a region is kind of a rare one, but this is going to create two tails of data, and you'll find the area there. So let's return to those ones that we calculated using the empirical rule and compare and contrast our answers, getting the exact values from Stapplet. So for part A, we want to find what percentage or probability of the time is annual rainfall between 32 and 48 inches. And this is where still drawing a little sketch can be really helpful, because as we move to technology, we want to make sure our understanding from us reading the problem matches up with our understanding of plugging into technology. So it doesn't have to be super detailed, but just drawing yourself a little sketch, and hopefully that will get you on the right track to kind of confirming your answer as you get it from technology. Okay, so between two values, 32 and 48, and we estimated that as about 68%. So now let's go find the exact value. So I set my mean and standard deviation, and this is going to be calculate the area between two values. So this will be between 32 and 48. I'm going to calculate that area, and this is where seeing the visual can be really nice, because that'll just match up. So I know I'm looking at the right area. And then the area is 68.27% would be our exact answer. So for this one, what we were finding is the probability. So for my probability notation, this would be like 32 less than or equal to my random variable x, less than or equal to 48. And that was a 68.27%. Again, my open math will sometimes want the decimal form, so you just have to translate between the two. To know whether or not it wants the decimal form, or rather, it's kind of easier to see. If it wants the percentage, the answer box will have the answer box and then a percent symbol next to it. But typically, all other times, it'll want the decimal. Okay, then for part B, we were asked to find what is the probability for more than 48 inches. And again, I believe I mentioned this video, but if I didn't, let's kind of talk through it again, of it being strictly more than versus more than or equal to does not matter here. So when I go to Stapplet and I want this area more than, so that's going to be an area to the right, and my cutoff value is going to be 48. Some students might think, well, it has to be more than 48, so I'm going to go 48.1 or something like that, or 0.01, but we don't need to move it at all. For this, a single line does not hold any value of area here, so the difference between 48 and 48.0001 is nothing. So with this, we can just use the values, and for this normal distribution, we don't need to worry about the difference between more than or equal to, like we did with the binomial and discrete random variable distributions. Okay, so area to the right, because we're looking for more than, and we have 48, and we're going to calculate that area of 15.87%. So for this one, our probability notation, we're looking for the probability X is more than 48, and we can write it like that. That is correct. You could even write it, if you just always want to use the more than or equal to or less than or equal to symbols, it's technically correct for just this section. And then the answer we got out was 15.87%. I'll go ahead and write that as a 0.1587 to see that decimal form. And then we would go make the sentence, we'd use the 15.87%. Just to emphasize, this is what we'll be using for the rest of the course for calculating area under the curve. Empirical rule was purely just to get kind of intuition with how these areas separate up. And so if you see that you're roughly 2 standard deviations away, you'll have an idea that you'll be close to 95%, but they're all estimates. So any questions where you're asked to find area under the curve, this is what we're using. Okay, part C, we're looking for 24 inches or less. So with this, we'll be looking for area to the left, and our cutoff is 24. And for that area, we get a 2.28%. To get my pictures matching up, and I'm also seeing that it's close to the answer that I got with the empirical rule, but this has more accuracy to it. So that was a 2.28%, less than or equal to 24. Okay, and then part D, where we looked for an annual rainfall of 54 inches or less. So with this one, this is where, and sorry, in the video I was still using a program called GeoGebra, but we are using Stapplet. And we'll go, so we're still doing less than, but now our cutoff is 54. And there's a 95.99%. Ooh, sorry. 95.99%. There we go. Okay, so there's our accurate values for the answers for that scenario. Let's take a look at another scenario here, just to deal with some different values. So we're going to have a mean of 1.75 and a standard deviation of 0.3. So we're going to define and draw the model. And then what I'm seeing are these questions that are asking for, what's the percentage? What's the percentage? And with those, I know I'm going to be finding area under the curve. So I'm just looking ahead at that so that I know which operation to be using. There may be questions where we have to switch between the two operations, and I'll just try to emphasize of when we're using which operation. Okay, so our model, if we have a random variable x, so x is representing cholesterol levels. And then x is defined by a normal curve with a mean of 1.75 and a standard deviation of 0.3. And with that, you can draw a picture, or if you want to copy and paste from Stapplet directly, that works great. So you can go ahead and do that. There's our distribution. I'm going to take a little screenshot of it and put that in my notes. And then what can be helpful about having the picture is you can then use it to help draw sketches for each question so that you know that your understanding is matching up. So in fact, I might even copy and paste a few of these so that I can use them to help answer the questions. All right, so we're all good for part A there. We defined our distribution, we have a picture to work with. And with this question, a child has a cholesterol level of 2.11 milligrams per milliliter. What is the percentage of children in Wisconsin who have cholesterol levels that are higher than this child's? So what we're going to do is look for a cutoff of 2.11, which is out here. And we want to find the area above because we're looking for cholesterol levels higher. So we want to find the probability that X is more than or equal to 2.11. And this is where we go to our program, and we're going to go area to the right, and we're going to put in 2.11. And that'll be an area of 11.51%. So we could say 11.51% of children in Wisconsin have cholesterol levels higher than 2.11 milligram per milliliter. Okay, with the next one, we want to find the percentage of children who have cholesterol levels between 1.3 and 2.23. So we're going to look for 1.3 and then 2.23. Just somewhere over there. And we want to find this area in between. So our empirical rule can help here, and I have the visual, but I'm like, okay, that's a little more than one standard deviation away, so maybe I'm like at 70-ish%. So I can get some intuition going before I plug anything in. So we're looking for the probability between 1.3 and 2.23. And we'll go for between two values, 1.3 for the left boundary, and the right boundary is going to be 2.23. And that's at 87.84%. So we could say 87.84% of children in Wisconsin have cholesterol levels between 1.3 and 2.23 milligrams per milliliter. Okay, so all of these are cases of given a cutoff value or cutoff values and finding the area kind of bounded by those cutoffs. What we want to do next is reverse this and look for, if we know the area under the curve, what's the cutoff value? And that's where we switch to our other operation.